Okay, so this is the last session of the theory portion of this chapter, very long, the longest chapter of the book, and let's see what, 4, according to Davies, first author of the text, 4 main postulates. So the core, the main ideas of quantum mechanics, and once you may not understand them intuitively, that's quite a challenge in quantum mechanics, but at least you've mastered them and you can manipulate them and play with them and so on, then you will be able to solve all kinds of problems in quantum mechanics in various domains. I'll talk a little bit about that at the very end. Okay, so probably one of the most basic ideas is that for each physical system that you have, there's a corresponding wave function or state function or state vector or ket. I mean, there's many ways to say this, right? Psi, and that psi contains all the information that you can know about the system. Now, it's probably that statement that's most contested by people who are not happy about the conventional interpretation of quantum mechanics. Remember, I've said quite a few times that the formalism of quantum mechanics is one thing. Interpreting what it means is quite another. And most people think the formalism works quite well, and in some ways spectacularly well. There are aspects of quantum mechanics that are accurate. You perform measurements, and the theory and the measurements match incredibly closely, like 1 part in 10 significant figures. So accurate to 1 part in 10 billion, that kind of thing. So quantum mechanics works very, very well, but the interpretation is hotly contested, even after, well, it's been a century now. So, this idea that it contains all the physical information that can be observed is what's contested. You had the famous debate in the 20s and 30s and onwards, till Einstein died, between Niels Bohr and Albert Einstein. On the one hand, you had one school of thought, the so-called Copenhagen interpretation, with on one side Bohr, of course, and his close followers, Heisenberg, Pauli, Born. It's Born of the Born probability density idea. And on the other hand, you had Einstein and de Broglie and Schrödinger and Bohm, my old physics prof when I was a young man, who didn't like the lack of determinism in quantum mechanics, that they didn't like that quantum mechanics is unable to tell what's happening to with a single system. They didn't like the idea of an inherent statistical interpretation of quantum mechanics. So, who knows? A century from now, where will quantum mechanics be? So, interesting question. Anyway, the conventional interpretation is that this psi function is all that you can know. It's the maximum amount that you can know about the system. Okay? And that this psi function satisfies the Schrödinger equation. It doesn't say in the text, but you need to keep in mind, unless it gets observed. Right? This is when it's undisturbed, so it just evolves according to the Schrödinger equation when it's not being disturbed. But when it is measured, that wave function here will collapse. But that's postulate 4. So when undisturbed, this psi function here evolves according to the Schrödinger equation. Right? Now, for every observable, remember, an observable is just some physical quantity that you can measure: energy, charge, mass, momentum, angular momentum, spin, whatever. Lots of observables in physics. So to each observable there's a corresponding Hermitian operator. and that operator gets used in the observable's corresponding eigenequation. Right? So the Hermitian operator times an eigenfunction is equal to an eigenvalue times the same eigenfunction, so the eigenequation. Right? And the eigenvalues are the possible measured values that you'll get. So for a given observable, and you measure it, you'll get usually discrete quantized values of that quantity, measurable quantity, that observable that you're talking about. And it's the eigenequation that tells you the values of the measured quantity. They are your eigenvalues. And they are the eigenvalues of the operator in your eigenequation that corresponds to the observable you're talking about, that you're measuring. Okay? I've said that many times now. I hope that's well and truly sunk in. Okay? Now, after the measurement, so you get a collapse. The wave function psi will collapse to one of the eigenstates in your eigenequation. Okay? So then the state of the system will not be psi. It'll be one of the eigenstates whose eigenvalue you actually measured. Right? The result, the measurement result, is one of the eigenvalues, and its corresponding eigenstate is the new state. So this psi here will collapse to that eigenstate. Right? Postulate 3, basic idea of quantum mechanics, is that when you're dealing with quantum mechanical systems, you need to keep in mind that in appropriate limits, as for example very high quantum numbers, as the energy values get higher and higher, this kind of thing, your quantum mechanical system needs to approach, merge, if you like, with the behavior of classical systems. Because at our scale of things, the human scale, we live in a classical world. So you don't want quantum mechanics in the limit approaching something that's wildly different from the world that we know, at human scale, at classical mechanics level. So the correspondence principle gets used quite a lot. There needs to be a correspondence, a smooth transition from one to the other, in a sense, between quantum mechanical systems and classical, in the limit as your quantum numbers take high or large values, or very small values. For example, if well, it depends on the context, but when Planck's constant, for example, in the limit goes to 0, then a lot of your quantum mechanical equations become the equivalent of behavior in classical mechanics. Stuff like that. That's the general idea of the correspondence principle. Right? Now, when you try to find the corresponding the operators for observables, now we've done this for the position operator. We just usually use r hat, and its eigenvalue is just the position, so it would just be r. And for the momentum, the observable, the corresponding momentum operator, so p hat, we found was minus IH bar del, del from vector calculus. Right? Now, it's actually the case. Now you'll notice next lecture in chapter 7, we will define angular momentum operators in terms of these two, and that's we'll use these two operators to define and create angular momentum operators, and then we'll put those angular momentum operators in their corresponding eigenequation and generate eigenvalues that correspond to allowed, discrete quantized angular momentum values for the system we're talking about. Right, and that's quite general. Often these two